Welcome back, everyone, to MAE170. This is lecture 10 in week number 5. So today we'll continue describing the root locus method. We arrived at step number 7. So far we saw how to draw just part of the root locus. Just as a quick recap of the previous steps, you have to write the characteristic equation of the closed loop transfer function in the canonical form, find the open loop zeros and the open loop poles, draw them on the S-plane, find the segments of the real axis that belong to the root locus, find the asymptotes if they exist, and draw them. So you have first to find the asymptote centroid, and then depending on how many asymptotes, they're going to be in a fixed configurations. If it's just one, then it's going to be the negative real axis. If there are two, they're going to be perpendicular to the real axis, and so on and so forth, as we saw last time. And now, in step number 7, we are ready to find the intersections of the root locus with the imaginary axis. In the example that we were seeing last time, we are predicting that the root locus will cross the imaginary axis. So how do we find exactly such intersections? Well, first of all, before addressing that, we have to realize that when the root locus crosses the real axis, the imaginary axis, so let's say that as k grows, we'll go this way. So we cross the imaginary axis from the left to the right. Once we cross the actual axis, our system transitions from being stable to unstable. Remember that these lines, the root locus branches, contain all the possible locations of the closed loop poles, and the closed loop poles will determine the stability of the system. So if we are on the left-hand side of the S-plane, our closed system is stable. Whereas if we are on the right-hand side, our closed system is unstable. So when we transition from one half to the other half of the S-plane, we change the stability of the system. Of course, you could also have that the direction of growth could go the other way. So if you had that as k grows, you follow these two branches from right to left, and the system becomes stable as k grows when it intersects the imaginary axis. So at the actual intersections, the system is marginally stable. So how do we actually compute such intersections? Well, we have a couple of strategies. We can use what we already know, the Routh-Hurwitz criterion. So using the Routh-Hurwitz criterion, we can find a critical value of k, which we're going to call k star, at which the transition occurs. Now that we have the specific value for k, that is k star, we can solve the characteristic equation using k equals k star. And remember, for what I said last time, solving the characteristic equation means that we have to solve two equations, one for the magnitude and one for the phase. So we're going to have, typically, if you just have 1 plus k times n of s over d of s equals 0, let's say that s is sigma plus I omega, then generally speaking, you have three unknowns to determine: K, sigma, and omega. In this case, we already have the value or the critical K, that is K star. So the only unknowns are omega and sigma. But there's actually only one unknown that we care of, because at the intersection, well, the points, the complex numbers at the intersections are simply imaginary numbers. So we're really looking at S that is just equal to I omega. So the points we're looking for are just imaginary numbers. That is, sigma is equal to 0, and therefore our only unknown is omega. The other strategy will just be solving directly the characteristic equation. So technically, as I just said, we would have three unknowns, but only two equations: the magnitude equation and the phase equation. But once again, since sigma has to be 0, then our only unknowns are omega and K star. So it's up to you. You can use either method A or method B. With method A, it's more step by step. You find one thing at a time. First, by using Routh-Hurwitz, you find the critical value for K, and then solving the characteristic equation, you find omega. By directly solving the characteristic equation instead, you're going to have a system of two equations in two unknowns, the two unknowns being omega and K star. So once again, solving the characteristic equation means solving 1 plus K times N over D equals 0, which in turns mean to solve two equations, one for the magnitude. So the magnitude of K times N over D has to be equal to the magnitude of -1, that is 1. And the phase of K N over D has to be equal to the phase of -1, which is 180 degrees, plus N 360. And of course, here you have to use S equals I omega, because we're interested in the intersections with the imaginary axis. So we're looking for solutions that are imaginary, not just general complex numbers. All right, so now that we have the intersections with the imaginary axis, and then we're going to see the computations in an example later on, we're ready to describe the next step, step number 8, which is to find the break-in or breakaway points. I've already described what break-in or breakaway points are, but let's review what they mean. So we have break-in or breakaway points when two or more branches of the root locus will merge in the real axis, or they collide coming on the real axis and they have to break away from it in the complex, in the rest of the S-plane. Let me just give you an example. For a second order system, we know that one branch starting from the imaginary axis will follow a semicircle and then will eventually hit the real axis at this point, which is S equals minus omega n. And then we can draw the corresponding branch on the other half of the plane, which once again starts on the imaginary axis and then will hit the real axis at S equals minus omega n. Now we have two branches that collide, and since they cannot coexist indefinitely, they can only coexist at one point, then they have to split. So the red point here is called break-in point because we're breaking in the real axis. So this is a break-in point. And then one of the two branches will go towards the right and the other one will go towards the left. It doesn't really matter which one. And so we can complete the root locus. So in this step, we want to calculate exactly the locations of these break-in or breakaway points. One thing that we can notice is that at these locations, the closed loop system will have poles with multiplicity that is greater than 1. That is, we have repeated poles. In fact, we already know that for a second order system, if we look at this example, at s equals minus omega n, well, we have, this occurs when zeta is equal to 1. So we have two real poles that coincide. So P1 is equal to P2, and they're both equal to minus omega n. So as I'm going to write here, at the break-in or breakaway points, we have repeated roots of the characteristic equation delta S equals 0. Or in other words, you can think about it as repeated closed loop poles. If they occur on the real axis, well, obviously they're going to be real poles. So a mathematical condition to find the break-in and breakaway points is developed as follows. I'm not going to go over the entire mathematical proof. I still wrote it down. So if you're curious, you can just go over it. And if you don't understand something, you can always ask me. But here the concept is that at the break-in or breakaway points, we can rewrite the characteristic polynomial as s plus a elevated at gamma times delta 1 s. And this means that we can factorize delta s into a lower order polynomial delta 1 of s, and then s plus a to the power of gamma means that s equals minus a is a repeated root with multiplicity equals gamma. And gamma is greater than 1. So it can be 2, 3, so on and so forth. So then here we have the start of the proof. So I'll just get to the bottom of it. You can prove that in order to have that condition, you have to satisfy this equation here, equation 4. So this equation is satisfied if either one of these three terms is equal to 0. Either one of these factors, I should say. So the first one being dk over ds equals 0, or we have n over d equals 0, or alternatively, simply n of s equals 0, or the third factor being 1 plus k times n over d equals 0. Well, let's just take a look at the last two. N of s equals 0. Well, those are just the open loop zeros, so they're not necessarily equal to the break-in or breakaway points. It still satisfies the equation, but if you just solve for n of s equals 0, you're just getting the open loop zeros. Then the second factor, 1 plus k times n over d equals 0, well, that is simply the characteristic equation itself. So that has to be satisfied no matter what. So it doesn't give us any extra information because all the points belonging to the root locus satisfy such equation. So there's nothing new. The new condition that we have instead is dk over ds equals 0. That is, the first derivative of k with respect to s is equal to 0. And this is the actual break-in or breakaway condition. So break-in or breakaway points are solutions to this equation. Now, there's a thing that you have to keep in mind, that not all the solutions of this equations are break-in or breakaway points. So in other words, dk over ds equals 0 is a necessary condition for a solution to be a break-in or breakaway point, but it's not necessary and sufficient. So you can think about it this way: a solution, or let's say the S is a break-in or breakaway point. So this implies that it is a solution to dk over ds equals 0. But a solution to dk over ds equals 0 does not imply that such solution is also a break-in or breakaway point. So you have to be careful when you solve this equation. You have to analyze all the solutions because some of them might not be feasible break-in or breakaway point. That's why you need your judgment is required. It's going to be quite clear anyway. However, you have to think about it. So do not go into it as robots. Just use your brain and your engineering judgment. Now, step 9. I wrote it down here, but I'm not going to cover it because it's quite lengthy, and I don't think it's strictly necessary for you to learn, because in the end, we can always retrieve the root locus using MATLAB. So, well, let me tell you what this step is all about. So this will determine the angle of departure of the root locus from open loop poles, or the angle of arrival to open loop zeros. So in other words, if you had, let's say in the complex plane, in step 2 or 3, I think 3, we mapped the open loop zeros and poles. And so let's consider this open loop pair of poles over here. Then you know that the root locus will start at this point because k is going to be equal to 0 at the open loop poles. But where does the root locus start? Will it start going this way, this way, this way, this way? You have an infinite amount of options. So, it could go this way, could go this way. You might know that, for instance, it will end up here, but will it follow this route, this route, this route, this? So how does it leave the open loop pole? Well, step 9 will give you a comprehensive way of finding the angle of departure from open loop poles, or angle of arrival if we're talking about open loop zeros. Again, you're more than welcome to take a look at it, but it's not going to be required. And as usual, if you have questions, please ask me. It's not as complicated as it might seem. But for now, I just want to skip that, and I want to focus on actual examples of the root locus. Before doing that, well, I want to conclude with step number 10, which is very easy, and we've already talked about. So step 10, you just have to identify the directions in which K grows using arrows, and possibly use different colors to highlight the different branches of the root locus. And we've done that already. So if you have 3 separate loci, then use 3 colors for the 3 branches. Just to keep in mind. And it's easier, it's mainly for you. And MATLAB does also that. If you use the RLocus function, so if G is your open loop transfer function, if you use this command RLocus of G, it will plot the root locus for the closed loop system, as in kg over 1 plus kg. And so it will use different colors for the different branches. All right, before actually seeing practical examples, I want to review one thing that I've already mentioned last time, and that is the arctangent function. You have to pay attention to the sign of the numerator and of the denominator. In this case, let's just take a look at these points that I've graphed over here. So when you have arctangent of 0 over something non-zero, which we're going to call A, well, this can be either 0 or 180 degrees. So if the denominator is positive, then you're going to have 0 degree. If the denominator instead is negative, then you're going to have 180, because you should think about the arctangent, or the argument of the arctangent, as sort of the imaginary part over the real part. So if A is negative, the real part is negative, so we are on the negative real axis. So the phase angle associated with such number has to be 180 degrees. Then if we instead have arctangent of B over 0 with B different than 0, well, we can have, so we have a imaginary part that is not 0, but we have the real part that is 0. So if we have a real part that is equal to 0, it means that we are on the imaginary axis. So arctangent of B over 0, it's technically arctangent of infinity. So which angle has the tangent that is equal to infinity? Well, it can be 2 angles. It can be 90 degrees if B is positive, so we are on the positive imaginary axis, or 270 degrees or minus 90 degrees if B is negative, that is, if the imaginary part is negative. And similarly, we can take a look at the arctangent of C over C. Now, if C is positive, so both real and imaginary parts are positive, then we're looking at 45-degree angle. But if both the numerator and the denominator, that is imaginary and real part respectively, are negative, then arctangent of C over C is 225 degrees. That is this point here. So once again, be careful when you use your calculator to compute the arctangent of an angle, because if you have arctangent of minus 2 over minus 2, if you just do minus 2 over minus 2, it is 1. And then you compute arctangent of 1, it will give you 45 degrees. But minus 2 is negative. So both numerator and denominator are negative. So you're actually looking at 225 degrees. So be careful. And lastly, if you have d over minus d, well, if d is positive, then, okay, imaginary part is positive and real part is negative. So the angle we're looking at is 135 degrees. And vice versa, if d is negative, then we're looking at this other angle, which is 315 degrees or minus 45 degrees. So you have to be careful when you use your calculator. Otherwise, you can avoid that when you're using MATLAB by selecting the function arctangent 2. So you have to actually write ATA and 2, and then the arguments are going to be the numerator, comma, denominator of the fraction. So you put first the imaginary part and then the real part. And of course, the result will be given in radians. If you want it in degrees, you can use ATN 2D, and then same numerator, comma, denominator. So it will track the sign. It will do that for you. But if you're just using a calculator, let me repeat it again. The only values that you will get will be between minus 90 and plus 90. So only on the first quadrant and the fourth quadrant. You will never get values in the second and third quadrant. So you have to be careful. And this is very important for this class. All right, with that being said, we're ready to take a look at an actual example. So here we are asked to find all the closed loop poles of the following closed loop system. So this is another way of saying draw the root locus, because by now you know it very well. The root locus represents all the possible locations of the closed loop poles. So here we have our standard closed loop system with the proportional controller K, and we have a plant or process transfer function that is s plus 1 squared over s cubed. So this represents our g of s, and therefore our closed loop transfer function is k times g of s over 1 plus k times g of s. So this is equal to k times s plus 1 squared over s cubed over 1 plus k times s plus 1 squared over s cubed. All right, before doing anything else, let's take a look at the characteristic polynomial, which is the denominator of t of s. It's 1 plus k times s plus 1 squared over s cubed. Is it in the canonical form? It is. So remember, the canonical form wants us to have the characteristic polynomial or characteristic equation once we equate it to 0 as 1 plus k times n over d. So that's exactly what we have here. So step 1 is already taken care of. What about step 2? Well, step 2, we have our g of s equals s plus 1 squared over s plus 3. Well, we have to factorize it and find the open loop zeros and poles. Well, it's already factorized. If you want, you can write it like this to be extremely clear, but it's pretty easy to see that the roots of the numerator are 2, so we have 2 zeros, and they're equal to -1. Sorry, let me just use z. So z1 is equal to z2, and they're both equal to -1. Well, we have -1 with multiplicity equal 2, so r is equal to 2, and we have 3 open loop poles at the origin, so they also all coincide and they're equal to 0. So with multiplicity equal 3, and L is equal to 3. Oh, actually here I've included step 3 and step 2. You see, as I told you last time, sometimes you can do 2 steps at once, but let me just write it down again. So we have the actual open loop poles at -1 and the open loop zeros. Sorry, the other way around. The open loop zeros at -1 and the open loop poles at the origin. And before drawing them on the S-plane, let's just complete also step 4, which is pretty straightforward. That is, how many separate loci do we have? Well, that's the maximum between R and L. That is the maximum between 2 and 3, which is 3. So we have 3 different branches. So we need 3 collars, okay? All right. So we're ready here to draw the open loop zeros and poles. Let's start with the poles. They are at the origin. So since there are 3 of them, I'm going to do something like this to indicate that we have 3 crosses at the origin. So we have 3 poles at s equals 0. And then we have 2 zeros at -1. So I'm going to draw them as 2 concentric circles to indicate that we have 2 zeros. If it is not clear, what you can do is just say we have 2 zeros at s equals -1. All right. Step 5, though, says that we need to identify the segments of the real axis that belong to the root locus. So now that we have the open loop poles and the open loop zeros on the S-plane, we can do exactly that. So swiping from the far right, going towards the left, we encounter at the origin 3 open loop poles. So 3 is an odd number. So it means that to the left of it, everything that is on the real axis belongs to the root locus. So we're going to select the segment until we find some other peculiar points. There we go. At -1, we encounter other 2 points. In this case, they're the 2 open loop zeros. So the total number of open loop poles plus zeros that we have so far at -1 is 5. 5 is also an odd number, so whatever lies to the left of it belongs to the root locus. And so we're going to select everything. And since we don't have any other open loop poles or zeros, then we know that all the negative real axes will belong to the root locus. So we're already expecting one asymptote to be on the negative real axis. And in fact, going to step 6, we actually need to find the asymptotes. So remember that we have asymptotes whenever we have more open loop poles than zeros or more open loop zeros than poles. So in other words, when we have a different amount of open loop zeros than poles. In this case, we have L that is equal to 3 and R that is equal to 2. So L minus R is 1. So we're going to have one asymptote. And so when we have only one asymptote, if we go back to the description of the asymptotes, there we go. When we have only one of them, well, that is the negative, it coincides with the real axis and takes, all the negative real axis. In this case, the centroid is not really necessary to compute, but we're going to do it anyway, just for exercise. So where's the location of the asymptote centroid? We need to add all the poles. So we have 0 plus 0 plus 0 minus all the zeros added up. So minus 1, divided by 1, because that's the difference between poles and zeros. So in this case, we have minus 2 over 1, that is 2. So technically, the asymptote centroid is at plus 2. So it would be somewhere around here. And as I said last time, the centroid does not necessarily belong to the root locus. And in fact, this does not belong to the root locus. Plus 2 does not belong to the root locus. The only real numbers belonging to the root locus are between 0 and minus infinity for this example. What about the angles of the asymptotes? Well, in this case, I should say the angle of the single asymptote. And when we only have one, the angle is always 180, which we already know. And in fact, when we're going to minus infinity. Now, step 7, intersections with the imaginary axis. Finally, we can do some more computations, because so far it has been quite straightforward. So this step is going to involve some more calculations. So as I said earlier, in order to find the intersections with the imaginary axis, we have two options. We can use the Routh-Hurwitz criterion and then solve the characteristic equations using the critical value for k, or directly solving the characteristic equation using, having to find k as well. So let's use the first methodology, that is, let's find the critical value of k using Routh-Hurwitz. So for Routh-Hurwitz, we need the characteristic equation or the characteristic polynomial written as an actual polynomial. So here we have it in the canonical form. So we have to reshape it. So let's multiply everything by s cubed. So we're going to have s cubed plus k times s plus 1 squared equals 0. And now we need to do one extra step. That is, we have s cubed plus ks squared plus 2ks plus k equals 0. And now we have the same characteristic equation, but now it is in the form that we need in order to implement the Routh-Hurwitz criterion. So let's construct the Routh array in the usual way. So first of all, we have to order the coefficients in the first two rows, starting from the coefficient of s cubed, which is 1. Then we go down, we place k, then diagonally up, we place 2k, and then down again, we have once again k. Now we're ready to find the next element of the Routh array, that is the green box. So this is equal to k times 2k, remember figure 8, k times 2k minus 1 times k, everything divided by k. We're considering these 4 entries here. All right, so what do we have? Well, we have that this is equal to 2k minus 1. So 2k minus 1. The next term here is 0 because we are considering these two terms and these two terms, which are zeros. So it's obviously 0. What about the last entry of the Routh array? Well, in order to calculate this, we need these 4 elements. Now we have a 0 at the bottom right corner, so our element will be the one above, that is k. And so we have the Routh array as in 1k, 2k minus 1, and once again k. So if we wanted the system to be stable, then we need all the elements to have the same sign. Since we have a plus 1 as the first term, then we need k to be greater than 0, and then 2k minus 1 to be greater than 0 as well. And of course, then we have the repeated k greater than 0 for the last term. So in other words, we want k that is greater than 1/2. So for values of k that are greater than 1/2, the system is asymptotically stable. And so if we have values of k less than 1/2, the system is unstable. So what happens that at k exactly equal to 1/2, we have the transition. So our k star is exactly 1/2. Now we are ready to solve the characteristic equation using k equals k star. So the characteristic equation, we can once again write it in the whichever form you want. You can use the Routh-Hurwitz form or the root locus form. I'm just going to use the root locus one. So we have 1 plus k times s plus 1 squared over s cubed equals 0. All right, so now we have to use k equals k star, which is equal to 1/2. And furthermore, we are looking for numbers for solutions that are on the imaginary axis. That is, s has to be equal to I omega. So we can rewrite the characteristic equation as 1 plus 1/2 times I omega plus 1 squared divided by I omega cubed equals 0. See here that we have only one unknown, that is omega, as promised. So how do we solve this equation? Well, we have to treat it as just a regular equation, even though it's a complex equation, obviously, because we have an imaginary unit. So let's see how this is solved if you don't recall how to do it. Well, let's multiply everything by I omega cubed. So we have I omega cubed plus 1/2, then I omega plus 1 squared equals 0. So I omega cubed is equal to minus I omega cubed. Then we have plus 1/2. I omega squared is minus omega squared plus 1 plus 2I omega equals 0. So we have minus I omega cubed minus omega squared over 2 plus 1/2 plus I omega equals 0. All right, so take a look now at the left-hand side. We have a complex number, and we can actually rearrange it as a real part. So 1/2 minus omega squared halves plus I that multiplies omega minus omega cubed equals 0. So you see that we have a real part, let's call it A, and an imaginary part B. So this has to be equal to 0. So 0 is technically 0 plus I times 0. So what you can do is you can equate A equals 0 and B equals 0. Let's do it over here. So we have 1/2 minus omega squared halves equals 0, and then omega minus omega cubed equals 0. And of course, the value of omega that you find, they have to satisfy both equations. All right, so if we solve the first one, we find that the solutions are omega equals plus or minus 1. And then the solutions to the second one are omega equals 0 and omega equals plus or minus 1. Since both have to be satisfied, then the only solutions are omega equals plus or minus 1. And finally, since we were looking for S equals I omega, what we're looking for is S equals I. But remember, once you have a complex number, you always have the complex conjugate. So we have two intersections, one at S equals plus I and the other one at S equals minus I. All right, so right here, I once again have the S-plane, so we can draw the intersections of the root locus with the imaginary axis. So they are here and here. So at this point, we have omega equals 1, and this happens when k is equal to 1/2. And down here, omega is equal to minus 1, but k is also equal to 1/2. All right, so before going to step 8, that is calculating break-in and breakaway points, let's try to predict if we actually are going to have break-in or breakaway points, and if so, where they might be. So in order to do that, let's proceed as following. We know that at the open loop poles, that is at the origin, k is equal to 0. And then at the open loop zeros, k is or goes towards plus infinity. So if we try already to draw the direction of growth of k on the root locus, well, we only have now the segments on the real axis. So we know that we're going to move away from the poles. So one branch must go this way. But here we have 3 open loop poles. So we had 3 branches starting from the origin, and only one can go to the left. So the other 2 must break away from the origin. So I'm assuming that the origin will be a solution to the breakaway condition, that is dk over ds equals 0. And the only way that these 2 branches starting from the origin can break away, well, it is, they cannot break away. Well, they have to, well, since they're called breakaway points, they have to break away from the real axis. So they must go away like this. And why have I chosen to draw them to the right and not to the left? Well, that's because we saw that with the Roth-Hurwitz criterion, as soon as k is a little bit over 0, specifically between 0 and a half, the system is unstable. So we have to be on the right-hand side of the complex plane. That's why the 2 branches will break away in this direction. And then I'm predicting that they will come back because they have to intersect the imaginary axis where we calculated. And that's all we know. What else do we know? We know that for very small numbers, we're going to have that one branch will follow the asymptote towards minus infinity. But we also know that the open loop zeros will have to receive branches of the root locus. In this case, we have 2 of them. So we have 2 branches that will end up at -1. Well, one is coming from 0. So that's fine. That's just one branch directly connecting 0 and -1. But the other branch has to come this way. And you see the problem now. We have a direction going to the left and then one arrow going to the right. So at one point in between, we must have a break-in point. So 2 branches must come in the real axis, and then one will go to the left and one will go to the right. And guess what? I'm assuming that the 2 branches are exactly the ones that departed from the origin. So, in other words, I'm expecting a break-in point somewhere to the left of -1. So to recap, I'm expecting a breakaway point at 0 and a break-in point somewhere to the left of -1. And so I would like you to try and develop this critical thinking, critical reasoning, because once you get the solutions of the break-in/breakaway condition, as I said earlier, you might find solutions that are not actually break-in or breakaway points. So you have to think about it. With that being said, let's go ahead and actually solve the break-in, breakaway condition. And that was dk over ds equal 0. So how do we proceed from here? Well, we always start from our characteristic equation, 1 plus k times s plus 1 squared over s cubed equals 0. And let's explicit k. So k is equal to minus s cubed over s plus 1 squared. So now the condition tells us that we need to take the derivative of k with respect to s. So dk over ds is equal to the derivative with respect to s of minus s cubed over s plus 1 squared. All right, so what's the derivative of this function? Well, we have minus, and then we have the derivative of the numerator, so 3s squared times the denominator, which is s plus 1 squared, minus the numerator times the derivative of the denominator, everything divided by the denominator squared, that is s plus 1 to the power of 4. And this has to be equal to 0. Now, before starting multiplying things, to recognize that we have a common factor as s plus 1. So we can already write it as s squared, because s squared belongs to both terms at the numerator, times s plus 1. So this will multiply 3 times s plus 1. And whatever we have left on the other term, which is 2s. So this has to be equal to 0. And so we have s squared times s plus 1. And here we have 3s minus 2s, so s plus 3 equals 0. All right, so we have 4 solutions to this equation. We have s equals 0 with multiplicity 2, then s equals to minus 1, and then s equal minus 3. So let's now consider all of them, and according to our reasoning earlier, let's select the ones that might be or might not be break-in or breakaway points. So we were expecting s equals 0 to be a breakaway point. And here you see it has multiplicity 2 because we have at 0, we have 3 branches that need to stem from 0. So the breakaway point is 3 minus 1, 2. And the breaking point, which will be over here, it's going to have multiplicity equal 1 because there are only 2 branches coming in. So multiplicity is equal to the number of branches minus 1. And that value is the minus 3. You see here we have an extra solution, s equals minus 1. But minus 1, it's simply the 2 open loop zeros. So technically, yes, it's a breaking point because you have the convergence of 2 branches, but it's not 2 complex branches coming in. So the point that we were looking for is at minus 3. All right, so we have at s equals 0, we have a breakaway point. And at s equals minus 3, we have a break-in point. All right, now that we have everything, we can finally draw the entire root locus using 3 colors. So we have, starting from the open loop poles where k is equal to 0, we start with one branch. Let's say, let's go downwards first, and we intersect the imaginary axis at minus I, or omega equals -1, and that happens for k equals 1/2. And then we travel all the way until we come back hitting the real axis at -3 at our break-in point. And then, of course, since we need to have symmetry, then the branch going up has to be symmetric. So kind of does the same and comes back to the real axis at -3. So one of the branches then will go to the left, and one will go to the right, looking for its friend, that is the open loop 0 at -1. I will stop there. And finally, the third branch is entirely on the real axis, going straight from 0 to -1. And so now we are left simply with indicating the direction of growth for k. So as k grows, we go this way on this branch, up this way on this branch, and then this way on this branch. Now, once we hit -3, then one branch will go to the right, eventually going to the open loop 0 at -1. And the other branch will just follow the negative real axis, which coincides with the asymptote, all the way to -infinity, looking for the open loop 0 that is in here. Then here I also have the calculations for the angle of departures from open loop poles and zeros. And just as a rule of thumb, one thing that I want you to know is that when you have two branches coming in the real axis, they always do so at a normal angle, so it's 90 degrees. If you have instead three branches, like the ones departing from the origin, they will do so kind of like the asymptotes at 60, 180, and -60. But if you didn't have this branch over here, let's say you had only two open loop poles at the origin, then they will go up perpendicularly at the 90 degrees. But again, this is, you'll acquire that with a little bit of practice. Okay, I'll finish here for this lecture. And please take a look at the other PDF that I posted that includes another example, step by step for a root locus, and then more other root locus graphs for second order and third order systems. And I'll probably make an extra video going over them briefly. If so, I will announce it. If not, we can take a look at together on Tuesday. And all right, this is all. Have a great weekend, and I'll see you on Tuesday for the live Q&A session on Zoom. You can use just the office hour link, and I'll be there. All right. That being said, have a great weekend and take care.